In this video, I'll be solving a more complicated question based on one of the problems that we solved with our LOL diagrams previously. So the previous problem was that a tray of water 20 degrees Celsius is placed in the freezer and turned into ice cubes at -8 degrees Celsius. So that was one that we were able to set up an LOL diagram and solve. And if you want to review this, you can go back to your notes to take a look at how we approached that. What we're going to add in this case is the fact that we are dealing with 36 grams of water to be used in the process, and now we're going to ask the question how much energy is actually lost during this process. We can use heating curves to help to solve the problem here. The way that we're going to do this is to look at the heating curve and try to find where we start and where we end along the heating curve. So let's take a look at our starting situation. We're dealing with a tray of water at 20 degrees Celsius. We would like to find where along the heating curve that would correspond to. In order to do so, we should think about, well, first off, this is going to be liquid water. It's 20 degrees Celsius. We also happen to know that it's going to fall between the melting and boiling points of water, 0 degrees and 100 degrees, respectively. So because of that, that tells us that we're going to fall into region 3 here. That's the region where it's just liquid, and it also corresponds to those temperatures between the melting and boiling point. Specifically, it looks like it would fall closer to the 2 end than the 4 end, because we know 20 is closer to 0 than it is to 100. Again, these values apply specifically to water, so if we had a different substance, we'd have to use its melting point and boiling point. But we're going to place it about there with the blue dot on that portion of the curve. We know that at the end it's going to turn into ice cubes at -8 degrees Celsius. The important thing here is ice cubes, we're talking about solid, and solid alone, so we're going to be dealing with region 1. And we also see that it is below the freezing point, or the melting point. Melting point is at 0, and since we're at -8, that puts us a little bit below there, and so I'll put another blue dot in region 1, just a little bit before region 2. So we are going to be trying to trace out the path along the curve to get from the 2 points that we marked at the beginning and the end for this situation. In order to solve this, we're going to have to set up multiple calculations. This is because we go through 3 different regions of the heating curve. For each region of the heating curve, we're going to need to set up a separate calculation. So let's start off with the portion that falls into region 3. We know that region 3 ends once we hit the melting point, and at that point it'll begin to start freezing, so changing from the liquid to the solid. This means that we're going from an initial temperature of 20 degrees down to 0 degrees, and it's going to be a liquid the full time. After that, we're going to be going through region 2, where the temperature remains the same. So at the beginning it is 0 degrees, and it's also 0 degrees at the end. But at the beginning it's liquid, and at the end it's going to be solid instead. Finally, we're going to take that 0 degree solid and cool it further to -8 degrees Celsius. And again, that's talking about our solid state of matter here. So this starts to show us the 3 calculations that we're going to need to set up. We have 2 dealing with temperature changes, 1 in the liquid state and 1 in the solid state, and then 1 change of state that we have to go through, or 1 phase change that we have to go through, in this case going from liquid to solid. Let's start with our first calculation in region 3, when we're going from water, liquid, at 20 degrees Celsius to its freezing point or melting point, 0 degrees Celsius. We know for this energy associated with the temperature change, we're going to need the specific heat, and for liquid water, that is 4.18 joules for every gram in degrees Celsius. We can also set up this calculation with dimensional analysis like we've done before. Since we have 36 grams of water, we'll multiply by that on top to cancel out the grams. And the temperature that we're interested in here is the temperature change. We're going from 20 degrees to 0, so that's a change of 20 degrees Celsius. That's how much we've changed by. We see that the units are set to cancel, and this will come out to 2,173.6 joules on our calculator. And accounting for the significant figures, since we had 0 is pretty much an exact value, since that was how the Celsius is defined. So looking at our 20 for the temperature, that's going to give us 2 sig figs. So we're going to have to round this to the hundreds place. But for now, I'm just going to underline that so that we don't do the rounding in the middle. Once we add all the values together at the end, we'll do our final rounding at that point. Next, let's go on to our second region. This was the newer material, where we found that we can calculate the energy associated with a change of state by using either the heat of fusion or the heat of vaporization. In this case, we're dealing with change between solid and liquid, and so we'll be dealing with the heat of fusion. For the water that we're dealing with, that is 334 joules for every gram. And again, on the basis of dimensional analysis, we will want to multiply this by the mass, 36 grams over 1. And that will give us the energy that we must lose in order for the liquid to go to a solid, which in this case comes out to about 12,024 joules. Again, accounting for the sig figs, we see that we're multiplying two values that each have 3 sig figs. And so that means that our answer should be precise out to 3 digits, which puts us in the hundreds place again. Finally, we have that one last temperature change. Now you may be wondering why we have to separate the two temperature changes, and that's because what we saw earlier, it showed that specific heat of ice and liquid water were not the same. We have a different specific heat now that we're going to have to work with, and that means that the value will be slightly different. We see that the specific heat of ice, solid water, is 2.03 joules for every gram and degree Celsius. And again, we can use dimensional analysis to set up the rest of the calculation with our mass of 36.0 grams. And our temperature change this time, again, it's the change between 0 and -8, and that's a change of 8 degrees. I'll put that over 1. And when we multiply this out, it comes out to 584.64 joules. Again, coming to the significant figures that we would deal with, we're limited by the 8 this time, which only has 1 sig fig, which brings us just to the hundreds place. At this point, we've set up all the calculations that we need to do. And if we think about this logically, we know that in order to go from our starting conditions of 20 degrees Celsius down to that ice at -8 degrees Celsius, we're going to have to do all 3 of these changes, meaning that what we're interested in is the total of all of the energy values that we calculated. So we will add these together, which brings us to a total of 14,782.24. That many joules. This is the point where we should account for our significant figures. Since we're doing addition, what we have to think about is the place value. And all of the numbers here, when we accounted for sig figs, we found that they should go out to the hundreds place, meaning we should round this to the hundreds place. When we do so, we come out with 14,800 joules. And that would be our final answer. that the water must lose this amount of energy in order to be converted from that tray of liquid water at 20 degrees Celsius into ice cubes at -8 degrees Celsius. This process will be very important going forward when we want to do more complex energy calculations. So setting up your heating curve, finding the initial and the final parts as we're going through it, tracing the path through the different regions and setting up a separate calculation for each region will be the strategy that you should use to successfully solve these problems.